Hello everyone, this is Srijit and welcome to MCAC 35 Advanced DBMS. Today we discuss more about parallel database systems. First, let's see inter-query parallelism. In inter-query parallelism, different queries or transactions execute in parallel with one another. Transaction throughput can be increased by this form of parallelism. However, the response time of individual transactions are no faster than they would be in the transactions were run in isolation. Thus, the primary use of inter-query parallelism is to scale up a transaction processing system to support a larger number of transactions per second. It's the easiest form of parallelism to support, particularly in a shared memory parallel database, because even sequential database systems support concurrent processing. Supporting inter-query parallelism is more complicated in a shared disk or shared nothing architecture. Processes have to perform some tasks, such as locking and logging in a coordinated fashion, and that requires that they pass messages to each other. A parallel database system must also ensure that two processes do not update the same data independently at the same time. Further, when a processor accesses or updates data, the database system must ensure that the processor has the latest version of the data in its buffer pool. This problem of ensuring that the version is the latest is known as the cache coherency problem. Next is the cache coherency protocol. Various protocols are available to guarantee cache coherency. Often, cache coherency protocols are integrated with concurrency control protocols so that their overhead is reduced. One such protocol for a shared disk system is as follows. First, before any read or write access to a page, a transaction locks the page in shared or exclusive mode as appropriate. Immediately after the transaction obtains either a shared or exclusive lock on a page, it also reads the most recent copy of the page from the shared disk. And before a transaction releases an exclusive lock on a page, it flushes the page to the shared disk, then it releases the lock. This protocol ensures that when a transaction sets a shared or exclusive lock on a page, it gets the current copy of the page. The shared disk protocols can be extended to shared nothing architecture by these schemes as follows. Each page has a home processor PI and it is stored on disk DI. When other processes want to read or write the page, they send a request to the home processor PI of the page, since they cannot directly communicate with the disk. The other actions are the same as in the shared disk protocol. Next is intra-query parallelism. We have seen inter-query parallelism where different queries or transactions execute in parallel with one another. It's used for better transaction throughput. Now let's see intra-query parallelism where execution of a single query in parallel on multiple processes and disks. Using intra-query parallelism is important for speeding up long-running queries. Consider a query that requires a relation to be sorted. Suppose that the relation has been partitioned across multiple disks by range partitioning on some attribute, and the sort is requested on the partitioning attribute. The sort operation can be implemented by sorting each partition in parallel, then concatenating the sorted partitions to get the final sorted relation. Thus, we can parallelize a query by parallelizing individual operations. There is another source of parallelism in evaluating a query. The operator tree for a query can contain multiple operations. We can parallelize the evaluation of the operator tree by evaluating in parallel some of the operations that do not depend on one another. Further, we may be able to pipeline the output of one operation to another operation. The two operations can be executed in parallel on separate processes, one generating output that is consumed by the other even as it is generated. Thus, we have two complementary forms of intra-query parallelism. First one is intra-operation parallelism, which parallelizes the execution of each individual operation such as sort, select, project, and join in the query. And we have inter-operation parallelism here execute the different operations in a query expression in parallel. The two forms of parallelism are complementary and can be used simultaneously on a query. The first form scales better with increasing parallelism because the number of tuples processed by each operation is typically more than the number of operations in a query. Now let's see parallel processing of some relational operations in intra-operation parallelism. To simplify the presentation of the algorithms, we assume that there are n processes P0, P1, etc. to Pn-1 and n disks D0, D1, etc. to Dn-1, where disk Di is associated with processor Pi. A real system may have multiple disks per processor. It is not hard to extend the algorithms to allow multiple disks per processor. We simply allow Di to be a set of disks. However, for simplicity, we assume here that Di is a single disk and we are using shared nothing architecture. Shared nothing architecture can be efficiently simulated on shared memory and shared systems. Algorithms for shared nothing system can thus be run on shared memory and shared disk systems. However, some optimization may be possible. Let's see parallel sort. Suppose that we wish to sort a relation that resides on n disks D0 etc. to Dn-1. If the relation has been range partitioned on the attributes on which it is to be sorted, then we can sort each partition separately and can concatenate the results to get the full sorted relation. Since the tuples are partitioned on n disks, the time required for reading the entire relation is reduced by parallel access. If the relation has been partitioned in any other way, we can sort it in one of the two ways. First, we can range partition it on the sort attributes and then sort each partition separately. Then we can use a parallel version of the external sort merge algorithm. Let's first see the range partition sort. Range partition sort works in two steps. First, range partitioning the relation, then sorting each partition separately. When we sort by range partitioning the relation, it is not necessary to range partition the relation on the same set of processes or disks as those on which the relation is stored. Suppose that we choose processes P0, P1, etc. to Pm, where m is less than n to sort the relation. There are two steps involved in this operation. First, create a range partition vector with m entries on the sorting attributes. Redistribute the relation using range partitioning. All tuples that lie in the ith range are sent to the processor Pi. Pi stores the tuples it received temporarily on disk Di. The step requires input and output and communication overhead. Each processor Pi sorts its partition of the relations locally. Each processor executes same operation, that is sort, in parallel with other processes without any interaction with the others. It is data parallelism. The final merge operation is trivial because the range partitioning in the first phase ensures that for 1 less than or equal to I less than j less than or equal to m, the key values in processor Pi are all less than the key values of Pj. Now let's see parallel external sort merge. Parallel external sort merge is an alternative to range partitioning. Parallel external sort merge then works this way. Assume the relation has already been partitioned among disks D0, D1, etc. to Dn-1, whatever manner. Each processor Pi locally sorts the data on disk Di. The sorted runs on each processor are then merged to get the final sorted output. The merging of the sorted runs in step 2 can be parallelized by this sequence of actions. The sorted partitions at each processor Pi are range partitioned across the processes P0, etc. to Pm-1, and each processor Pi performs a merge on the streams as they are received to get a single sorted run. The sorted runs on processes P0 to Pm-1 are concatenated to get the final result. This sequence of actions results in an interesting form of execution queue, since at first every processor sends all blocks of partition 0 to P0, then every processor sends all blocks of partitions 1 to P1, and so on. Thus, while sending happens in parallel, receiving tuples becomes sequential. First, only P0 receives tuples, then only P1 receives tuples, and so on. To avoid this problem, each processor repeatedly sends a block of data to each partition. In other words, each processor sends the first block of every partition, then sends the second block of every partition, and so on. As a result, all processors receive data in parallel. Next, let's see parallel join. The join operation requires that the system test pairs of tuples to see whether they satisfy the join condition. If they do, the system adds the pair to join output. Parallel join algorithms attempts to split the pairs to be tested over several processes. Each processor then computes part of the join locally, then the system collects the results from each processor to produce the final result. The partition join. For equijoins and natural joins, it is possible to partition the two input relations across the processors and compute the join locally at each processor. Suppose that we are using n processors and that the relations to be joined are R and S. Partition joins then works this way. The system partitions the relations R and S each into n partitions denoted by R0, R1, etc. to Rn-1 and S0, S1, etc. to Sn-1. The system sends partitions Ri and Si to the processor Pi, where their join is computed locally. The partition join technique works correctly only if the join is an equijoin. For example, R equijoins S, and if the partition R and S by the same partitioning function on their join on other join attributes. We can use either range partitioning or hash partitioning on the join attributes here. In either case, the same partitioning function must be used for both relations. For range partitioning, the same partition vector must be used for both relations. For hash partitioning, the same hash function must be used on both relations. Once the relations are partitioned, we can use any join technique locally at each processor Pi to compute the join of Ri and Si. For example, hash join, merge join, or nested loop join could be used. Thus, we can use partitioning to parallelize any join technique. Figure shows the partition join process. If one or both of the relations R and S are already partitioned on the join, the work needed for partitioning is reduced greatly. If the relations are not partitioned or are partitioned on attributes other than the join attributes, then the tuples need to be repartitioned. Each processor Pi reads in the tuples on disk Di, computes for each tuple T the partition J to which T belongs, and sends tuple T to the processor Pj. Processor Pj stores the tuples on disk Dj. Fragment and replicate join. Partitioning is not applicable to all types of joins. For instance, if the join condition is an inequality, such as R joins S where R dot A is less than S dot B, it is possible that all tuples in R join with some tuples in S and vice versa. Thus, there may be no easy way of partitioning R and S so that tuples in partition Ri join with only tuples in partition Si. We can parallelize such joins by using a technique called fragment and replicate. We first consider a special case of fragment and replicate, that is asymmetric fragment and replicate join, which works as follows. First, the system partitions one of the relations, say R. Any partitioning technique can be used on R, including round-robin partitioning. Secondly, the system replicates the other relation S across all the processes. In third step, Processor Pi then locally computes the join of Ri with all of S using any join technique. The following figure shows the fragment and replicate join. General case of fragment and replicate join. The system partitions the relations R into n partitions, R0, R1, etc. to Rn minus 1, and partitions S into m partitions, say S0, S1 to Sm minus 1. As before, any partition technique may be used on R and S. The values of m and n do not need to be equal, but they must be chosen so that there are at least m into n processes. Asymmetric fragment and a replicate is simply a special case of general fragment and a replicate, where m is equal to 1. Fragment and a replicate reduces the sizes of the relations at each processor compared to asymmetric fragment and replicate. Let the processes be P00, P01, etc. to P0m-1, P10, etc. to Pn-1, m-1. Processes Pij computes the join of Ri with Sj. Each processor must get those tuples in the partitions on which it works. To accomplish this, the system replicates Ri to processes Pi0, Pi1, etc. to Pim-1, which form a row in the above figure, and replicates Si to processes P0i, P1i, etc. to Pn-1i, which form a column in the above figure. Any join technique can be used at each processor Pij. Fragment and replicate works with any join condition. Since every tuple in R can be tested with every tuple in S, thus it can be used where partitioning cannot be. Fragment and replicate usually has a higher cost than partitioning when both relations are of roughly the same size. If one of the relations, say S, is small, it may be cheaper to replicate S across all processes rather than to repartition R and S on the join attributes. In such a case, asymmetric fragment and replicate is preferable even though partitioning could be used. Now let's see partitioned parallel hash join. The partitioned hash join can be parallelized. Suppose that we have n processes P0, P1, etc. to Pm-1 and two relations R and S such that the relations R and S are partitioned across multiple disks. The smaller relation is chosen as the build relation. If the size of the S is less than that of R, the parallel hash join algorithm proceeds this way. Assume S is smaller than R and therefore S is chosen as the build relation. A hash function h1 takes the join attribute value of each tuple in S and maps this tuple to one of the n processors. Each processor Pi reads the tuples of S that are on its disk Di and sends each tuple to the appropriate processor based on hash function h1. Let Si denotes the tuple of relation S that are sent to the processor Pi. As tuples of relations S are received at the destination processors, they are partitioned further using another hash function h2, which is used to compute the hash join locally. Once the tuples of S have been distributed, the larger relation R is redistributed across the m processes using the hash function h1. Let Ri denote the tuples of relation R that are sent to processor Pi. As the R tuples are received at the destination processes, they are repartitioned using the function h2. Each processor Pi executes the build and probe phases of the hash join algorithm on the local partitions Ri and S of R and S to produce a partition of the final results of the hash join. Note that hash join optimization can be applied to the parallel case. For example, the hybrid hash join algorithm can be used to cache some of the incoming tuples in memory and avoid the cost of writing them and reading them back in. Next, let's see parallel nested loop join. To illustrate the use of fragment and replicate based parallelization, let's see here we assume that relation S is much smaller than relation R and that R is stored by partitioning. There is an index on a join attribute of relation R at each of the partitions of relation R. Use asymmetric fragment and replicate with the relation S being replicated and using the existing partition of relation R. Each processor Pj where a partition of relation S is stored reads the tuples of relation S stored in Dj and replicates the tuples to every other processor Pi. At the end of this phase, relation S is replicated at all sites that store tuples of relation R, and each processor Pi performs an indexed nesting loop join of relation S with the ith partition of relation R. See some other relational operations. The evaluation of other relational operations are also can be parallelized. First example is the selection operation, sigma of theta on relation R. If theta is of the form AI is equal to V, where AI is an attribute and V a value, then if R is partitioned on AI, the selection is performed at a single processor. If theta is of the form L less than or equal to AI less than or equal to U, that is theta is a range selection and the relation has been range partitioned on AI, selection is performed at each processor whose partition overlaps with the specified range of values. In all other cases, the selection is performed in parallel at all the processors. Then next is duplicate elimination. We can perform by using either of a parallel sort techniques. Can eliminate duplicates as soon as they are found during sorting. Can also partition the tuples using either range or hash partitioning and perform duplicate elimination locally at each processor. Then projection operation. Projection without duplicate elimination can be performed as tuples are read in from disk in parallel. If duplicate elimination is required, any of the above duplicate elimination techniques can be used. Grouping or aggregation operation. We can parallelize the operation by partitioning the relation on the grouping attributes and then compute the aggregate values locally at each processor. This can reduce cost of transferring tuples during partitioning by partly computing aggregate values before partitioning. Consider the sum aggregation operation. Perform aggregation operation at each processor Pi on those tuples stored on disk Di. Results in tuples with partial sums at each processor. The result of the local aggregation is partitioned on the grouping attributes and the aggregation performed again at each processor Pi to get the final result. Fewer tuples need to be sent to other processors during partitioning in this technique. Next, let's see the cost of parallel evaluation of operations. If there is no skew in the partitioning and there is no overhead due to the parallel evaluation, expected speedup will be 1 by n, where n is the number of parallel processes. If skew and other overheads are also to be taken into account, the time taken by a parallel operation can be estimated as t part plus t asm plus max of t0, t1, etc. to tn minus 1, where t part is the time for partitioning the relations, t asm is the time for assembling the result, and ti is the time taken for the operation at processor Pi. This need to be estimated taking into account the skew and the time wasted in contentions. Now let's see interoperator parallelism. There are two forms of interoperation parallelism. First one is pipeline parallelism and second independent parallelism. Let's see pipeline parallelism. In pipelining, the output tuples of one operation, say A, are consumed by a second operation, say B, even before the first operation has produced the entire set of tuples in its output. The major advantage of pipeline execution in a sequential evaluation is that we can carry out a sequence of such operations without writing any of the intermediate results to disk. It is possible to run operations A and B simultaneously on different processes so that B consumes tuples in parallel with A producing them. This form of parallelism is called pipeline parallelism. Consider a join of four relations: R1 join R2 join R3 join R4. We can set up a pipeline that allows the three joins to be computed in parallel. Suppose processor P1 is assigned to the computation of temp as R1 join R2 and P2 is assigned to the computation of R3 join temp1 as P1 computes tuples in R1 join R2. It makes these tuples available to processor P2. Thus P2 has available to its sum of the tuples in R1 join R2 before P1 has finished its computation. P2 can use those tuples that are available to begin computation of temp1 join R3 even before R1 joins R2 is fully computed by P1. Likewise, as P2 computes tuples in R1 join R2 join R3, it makes these tuples available to P3, which computes the join of these tuples with R4. Now let's see the factors limiting utility of pipeline parallelism. Pipeline parallelism is useful since it avoids writing intermediate results to the disk. It is useful with a small number of processes but does not scale up well. First, pipeline chains generally do not attain sufficient length to provide a high degree of parallelism. Second, it is not possible to pipeline relational operations that do not produce output until all inputs have been accessed, such as the set difference operation, aggregate and sort, etc. Third, only marginal speedups is obtained for the frequent cases in which the operator's execution cost is much higher than are those of the others. Next, let's see independent parallelism. Operations in a query expression that do not depend on one another can be executed in parallel. This form of parallelism is called independent parallelism. Consider the join of R1 joins R2 joins R3 joins R4. Clearly, we can compute temp1 as R1 joins R2 in parallel with the temp2 as R3 join R4. When these two computations complete, we compute temp1 join temp2. To obtain further parallelism, we can pipeline the tuples in temp1 and temp2 into the computation of temp1 join temp2, which is itself carried out by a parallel join. Like pipeline parallelism, independent parallelism does not provide a huge degree of parallelism and is less useful in a highly parallel system, although it is useful with a lower degree of parallelism. Now let's see design of parallel systems. Since large-scale parallel database systems are used primarily for storing large volumes of data and for processing decision support queries on those data, parallel loading of data from external sources is an important requirement if we are to handle large volumes of incoming data. A large parallel database system must also address these availability issues. First one, resilience to failure of some processes or disks. With a large number of processes and disks, the probability that at least one processor or disk will malfunction is significantly greater than in a single processor system with one disk. A poorly designed parallel system will stop functioning if any component, maybe a processor or disk, fails. Assuming that the probability of failure of a single processor or disk is small, the probability of failure of the system goes up linearly with the number of processes and disks. Therefore, large-scale parallel database systems such as Teradata and IBM Informix XPS are designed to operate even if a processor or disk fails. Data are replicated across at least two processes. If a processor fails, the data that it stored can still be accessed from the other processes. The system keeps track of failed processes and distributes the work among functioning processes. Requests for data stored at the failed site are automatically routed to the backup sites that store the replica of the data. Next, online reorganization of data and schema changes. Online reorganization of data and schema changes must be supported. For example, index construction on terabyte database can take hours or days even on a parallel system. So it's need to allow other processing, that is insertions, deletions, updations, to be performed on relation even as index is being constructed. The basic idea of index construction tracks changes and catches up on changes at the end. It also needs support for online repartitioning and schema changes. So they are executed concurrently with other processing. Thank you for listening to my class on parallel systems. We will continue with the distributed systems in the next class.